Hello, I am Mohammed Ammar, a BTech student of Electronics and Communication Engineering at Central University of Karnataka. In this video, I am going to walk you through the EV ADAS dashboard project that I have built during my embedded systems internship. Over the 11 days, I went from blinking a single LED to building a full electric vehicle dashboard with collision warning, blind spot detection, fault handling, and a live Python visualization, all running on a simulated STM32F103C86 microcontroller based Blue Pill microcontroller board inside the Pixim lab. Let me take you through it day by day with all the technical details. Here's everything I'll cover, from basic GPIO control on day 2 through analog sensing, timers, and full EV physics model with ADAS safety logic, fault handling, and UART protocol, and finally a live Python dashboard. Let's get into it. So on day 1, my instructor introduced the entire project. We went through EV ADAS requirements and design documents version together in detail. This document defines the scope, real-time EV sensing at 10 Hz, ADAS safety features using 3 HCSR04 ultrasonic sensors, a deterministic vehicle state machine, telemetry streaming over UART, a priority tiered alarm system, and a fault management with a watchdog. The target hardware is STM32F103C86, also known as the Blue Pill board. It's built around a 72 MHz ARM Cortex M3 core with 64 kilobytes of memory, 64 kilobytes of flash memory, and 20 kilobytes of SRAM. Since we didn't have physical hardware, we used Pixim Lab to simulate the entire board. We installed STM32Cube IDE for writing and building the firmware, and set up Python 3 with PySerial and Matplotlib for the dashboard side. By the end of day 1, I understood the full data flow. Sensors feed into STM32, which runs the EV control and ADAS engine logic. Stream that data over UART at 115,200 baud rate. A Python dashboard, on the other hand, that will visualize everything live. On day 2, it was a hands-on. So first, on some background, ARM has three main processor profiles: Cortex A for high performance application processes like smartphone, Cortex R for real-time safety and critical systems like automotive ECUs, and Cortex M for microcontrollers used in IoT and embedded control. STM32 F1 series specifically uses a Cortex M3 core running up to 72 MHz without a DSP or floating point unit, which makes it ideal for LEDs, sensors, and communication tasks. Exactly what this project needs. We also covered a host versus target concept, my laptop running STM32Cube IDE host, and the Pixim lab simulating the STM32 Blue Pill board is the target. The Blue Pill has 48 pins total, but only 37 are usable IOs, spread across port A with 16 pins, port B with 16 pins, port C with just 3 pins, from PC13 to PC15, and port D with 2 pins. For the actual exercise, I configured PC13, which drives the onboard LED as a GPIO output in push pull mode. Then in the main loop, I called Hall GPIO toggle pin. So yeah, HAL underscore GPIO underscore toggle pin on the GPIO pin 13, followed by Hall delay of 500 milliseconds inside a while loop. Uh, I built this project in the Cube IDE, generated the binary file, loaded it into the Pixim lab, and ran it. So yeah, in the simulation, the LED blinked for exactly 500 milliseconds rate that I had set. On day 3, uh, we were introduced to analog sensing. I wired up 4 potentiometers in Pixim lab to simulate 4 real EV sensors. The accelerator pedal or pin A0, the brake pedal on PA1, the battery state of charge on PA2, and the motor temperature on PA3. I configured analog to digital converter as a 12-bit converter, meaning every reading comes back as a value between 0 and 4095, that is 4095, with a reference voltage of 3.3 volts. The conversion formula is straightforward. ADC value equals input voltage divided by 3.3 multiplied by 4095. So for example, 1.65 volts is exactly half of 3.3 volts, gives an ADC reading of 2047 or 50%. One more detail, Pixim Lab doesn't support scanning multiple ADC channels at once, so I had to read one channel at a time. For each channel, the sequence is call HAL underscore ADC underscore config channel to select the pin. HAL underscore ADC underscore start to begin the conversation, and HAL underscore ADC underscore poll for conversion with a 100 millisecond timeout to wait for finish. Then HAL ADC get value to read the result, and finally HAL ADC stop. Once I read the values, I scaled them into meaningful units, multiplying by 100 over 4095 to get 0 to 100% for accelerator, brake, SOC, that is the status of charge, and the motor temperature, and by 150 over 4095 to get 0 to 150 degrees Celsius for motor temperature. I then printed all 4 values over UART at 115200 baud rate, 8 data bits, no parity, 1 stop bit, using sprintf and HAL UART transmit, and confirmed on the Pixim Lab virtual terminal that moving each potentiometer updated its corresponding value live. For example, showing something like acceleration equals 45%, brake equals 0%, SOC 78, and temperature 65 degrees. Yeah. So this was everything that we covered on day 3. On day 4, we moved into distance sensing with a single HC SR04 ultrasonic sensor. I configured PA0 as the trigger pin, a GPIO output, and PA1 as the echo pin, a GPIO input. For accurate timing, I configured timer 2 as free running counter with a prescaler of 71, since the blue pills timer clock runs at 72 MHz. Dividing by 72 gives exactly 1 MHz tick rate, meaning each timer counter represents exactly 1 microsecond. The trigger sequence works like this: pull the trigger pin low, wait for 2 microsecond, then pull it high for exactly 10 microsecond, then pull it low again. That 10 microsecond pulse causes the sensor to emit a burst of ultrasonic sound at 40 kHz. The echo pin then goes high the instant the pulse is sent out, and stays high until the reflected sound wave comes back. I captured the timer 2 counter value the moment the echo goes high, that's my start time, and again the moment echo goes low, that's my stop time. The difference between those two gives me the pulse width in microseconds, which represents the total round trip time of the sound wave. To convert that into distance, I multiply the pulse time by 0.0343, that's the speed of the sound in centimeters per microsecond, and then divided it by 2 because the sound travels to the object and back. So dividing by 2 gives us the one-way distance. I clamped the result to the sensor's valid range of 2 to 400 centimeters with a 30 millisecond timeout in case no echo returns. I printed the resulting distance over UART and watched it update as I changed the simulated object distance in the Pixim lab. As I changed the position of the lever uh, in the Pixim lab of the ultrasonic sensor. Okay. On day 5, we learned about timers and interrupts using the embedded way. So using hardware timers and interrupts instead of the blocking delays. Up until now, blinking LED meant calling halt delay, which just ties up the CPU doing nothing useful while it waits. Instead, I configured timer 1 with a prescaler of 7199 and an auto reload period of 9999. Counting up. The update frequency formula is time 1 clock divided by prescaler plus 1 times period plus 1. Plugging in the numbers 72 million divided by 7200 times 10,000, which is 72 million divided by 72 million, giving exactly 1 hertz. So the timer fires an interrupt once every second. I started the timer in an interrupt mode using halt time base start it and implemented the halt time period elapsed callback function. Inside it, I checked that the interrupt actually came from timer 1 and then toggled the PC13. The result is the same blinking LED as day 2, but now the main while loop is completely empty. The blinking happens automatically through interrupt in the background, freeing up the CPU. I also initialized a second timer, timer 3, with a prescaler of 7199 and a period of 999 to prepare a faster periodic task later in the project. So that is known as the auto reload value. Auto reload value. Yeah. Moving on to day 6. Uh, we used multiple different files uh, to integrate different parts to integrate the project. In that we have the EV control.c and the EV control.h. So this is the vehicle's physics brain. Using these exact formulas given in the project's design document. First up, the torque. Motor torque equals throttle percentage divided by 100 times the maximum torque of 200 Newton meters times a mode scale factor. In echo mode, scales by 0.6, giving a peak of 120 Newton meters, which is best for range. Normal mode scales by 1, giving the full 200 Newton meters. Sports mode scales by 1.3, boosting the torque but clamped at 200 Newton meter maximum for sharp acceleration. Next is the regenerative braking. Whenever the brake pedal goes above the 5% threshold, I calculate a regenerative value as a brake percentage times 0.7 and the motor torque becomes negative. Specifically, minus regeneration value over 100 times the regeneration maximum of 80 Newton meters. So at full brake, that's minus 56 Newton meters of braking torque, which recovers energy back into the battery instead of wasting it as heat, and the status of charge goes high. So the battery increases because of the regenerative braking. For speed, I used a lumped inertia model with Euler integration. First, I calculate drag in Newton meters as speed in meters per second times a drag coefficient of 5. Then acceleration equals torque minus drag divided by mass factor of 450 kilogram meters, representing the vehicle's effective inertia. Finally, the speed in kilometers per hour is updated by adding acceleration times the time step times 3.6 and clamped between 0 and 200 kilometers per hour. So on day 6 we, by using the different files evcontrol.c and evcontrol.h, we prepared the what we call the brain of this project. Yeah. So UART telemetry printed once per every 100 seconds So we printed the speed, the SOC, the torque, the temperature, the range, the acceleration, and the braking percentage on in a line format on the virtual term, and we got the results. We verified all this in the Pixim lab. Continuing on day 6 also, motor powered, we did motor powered calculation. Mechanical power in kilowatts equal times mechanical power in kilowatts equals torque times speed in meter per second divided by 100 divided by 1000. I also added a copper loss term calculated as the torque ratio, torque divided by max torque squared. So these are all the formulas that we have used. Yeah. All of this runs on a timer 1 interrupt flag firing every 10 milliseconds, which triggers reading the ADC and updating the entire EV model completely non-blocking. Every second I print the full telemetry line over UART. Yeah, so we printed the speed, SOC, torque, temperature, range, accelerator, and brake percentages, and confirm all the values by changing the values of the potentiometer. On day 7, I expanded the ultrasonic sensor from day 4 into a complete 3 sensor setup, that is the front. Yeah, so on day 4, uh, I configured 3 ultrasonic sensor front, left, and right to give vehicle full awareness of the obstacles ahead and the vehicles in its blind spot. The front sensor's trigger and echo pins are PB0, PB1. The left sensor uses PB2 for trigger, PB3 for echo, and the right sensor uses PB4 for trigger and PB5 for echo. I used the exact same timer 2 microsecond timing approach from day 4, just extended it to read all 3 sensors one after the other with 60 millisecond gap between between each reading to avoid acoustic crosstalk between the sensors, meaning one sensor's echo doesn't get picked up by another. Each reading gets clamped into the valid 2 to 400 centimeter range. After generating the firmware and loading it into Pixim Lab, I tested by changing each sensor's simulated distance and confirmed. And we printed the front, left, and right distance simultaneously on the virtual terminal in Pixim Lab. On day 8, I turned those 3 distance readings into real safety features, the ADAS engine. Yeah, so we also incorporated 2 more files, that is the ADAS.c and ADAS.h. ADAS.c is the source file and ADAS.h is the header file that we included. So it contains the logic of collision and blind spot safety logic. Yeah, so first time to collision, I calculate as the front distance in meters divided by the current vehicle speed in meters per second. If the vehicle isn't moving or there's no obstacle within 2 meters, time to collision defaults to a safe 99.9 seconds, so it doesn't trigger false alarms. Based on time to collision and distance, I implemented 2 collision alarm levels. Warning trigger when front distance drops below 50 centimeter or time to collision drops below 3 seconds. A critical alert trigger when front distance drops below 20 centimeter or time to collision drops below 1.5 seconds. For blind spot detection, I compared the left and the right distance against a 30 centimeter threshold, but only when the vehicle speed is about 20 km per hour. So it doesn't falsely trigger while parked. Below 10 km per hour, the system instead switches to parking assist mode using all 3 sensors. Every alarm condition passes through hysteresis check, requiring 3 consecutive readings or 300 milliseconds before the alarm start actually flips. Overall, alarm priority works like P0 is none, P1 is advisory for blind spots or overspeed above 120 kilometers per hour, P2 is warning, and P3 is critical. These map directly to LEDs. PB8 lights up for collision warning or critical, PB9 for a left blind spot detection, and PB10 for right blind spot detection. Yeah. On day 8, on day on day 9 vehicle, we incorporated the state machines and the fault manager. We also included further the files, that is fault c, fault.c source file, and fault.h header file. So in that, in day 9 we focused on the states of the vehicle. Finite state machine, we designed the finite state machines in the fault manager. The vehicle has 5 states: parked, ready, driving, and region, and fault. The transitions are specific. Parked moves to ready on the accelerator pedal. Once the accelerator pedals exceeds 2%, ready moves to driving. Once the accelerator exceeds 5%, driving we move the driving moves to regeneration. Okay. So uh, the vehicle moves from parked to ready once the accelerator pedal exceeds 2%, and we move from the ready state to the driving state once the accelerator exceeds 5%. Driving moves to regeneration state when the brake pedal exceeds 10%, and the regeneration returns to driving once the brake drops back below 5%. But from any state, a critical fault forces an immediate jump to fault state. Specifically, when motor is overheated above 90 degrees Celsius, or the battery SOC is dropping below 2%, or a critical collision warning, then it triggers the fault state. I implemented this using a bit mask fault register, so multiple faults can be active at the same time. Fault OT for overheat, fault SOC for low battery, and fault collision for collision critical. When any of these flags is set, the firmware immediately cuts the motor's PWM output to 0, forces the state machine into fault, and latches a yellow LED on PB11. So a yellow LED is connected onto PB11, so it flashes when the vehicle enters a fault state. I tested this by injecting a simulated motor temperature and battery SOC beyond their threshold, and confirmed that PB11 fault LED turned on, and the motor PWM was cut within a single control loop cycle. There is also a fault clear function that resets all the flags, restores saved default values, and returns the vehicle to the parked state. On day 10, UART command shell, I built a UART command shell. So yeah, we included two of these files, that is the UART shell.c, that is the source file, and UART shell.h, that is the header file. So we updated the live diagnostics over serial port. We built a full command shell over the USART protocol, USART1, by using a bitrate of 115,200 with an interrupt driven ring buffer RX that captures incoming bytes as they arrive, and a command parser that handles typed commands. There is a print underscore status command that dumps the complete system state, that includes EV metrics, ADAS distances, and alarm level, and fault flags, all in one readable block. I can set the drive mode directly with mode echo, mode normal, or mode sport. I can inject the test values with speed set, SOC set, and temp set to test the EV model deterministically without moving the potentiometers. I can inject a fake obstacle distance with obstacle followed by a number to test the ADAS alarms on demand, or clear it with obstacle clear. I can force specific fault with fault inject motor, or fault inject SOC, or fault inject collision, that is, and recover with fault clear. And there is a general status reset and help command rounding out the shell. By the end of day 10, I had fully tested the UART protocol, ready to transfer data reliably. The next step, which I did right after, was writing a Python script to receive and visualize all of it. On day 11, we finally completed our project by making a Python dashboard. On day 11, we brought everything together visually. I wrote ev underscore python underscore dashboard dot py using matplotlib with backend for with tk ag for rendering, and PySerial to read data over a COM port connected to the same UART stream coming out of the Pixim lab. A background thread serial reader continuously reads incoming lines from the serial port. Each line gets parsed by a parse underscore line function using regular expression, and the result update a shared live state dictionary. From there, I built several dashboard panel, all refreshed in real time using Matplotlib's function animation. A speedometer with 0 to 200 km per hour arc and a needle colored coded from green through amber to red as the speed increases. A battery panel showing the state of charge as a horizontal bar along with the estimated range and the current drive mode. A speed history panel showing a rolling line chart of recent speed. A vehicle status panel listing the torque, accelerator, brake percentage, motor temperature, and all the three sensors, plus the fault state and connection status. And finally, an ADAS bird's eye view, a top down look at the vehicle shown in blue with color coded boxes. Yeah, and it shows the left and the right blind spots. There's a demo mode built in, so the dashboard can run and be demonstrated even without hardware connected. Okay. So that's the complete journey from, yeah, these are all that I've talked about. Yeah. So the Pixim Lab firmware, it loads it into the UART uh, along with the Python parser. It transfers the data into the live dashboard refreshed via matplotlib func animation. From LED blink to full EV ADAS system, we went from the GPIO timers, we blinked the PC13 LED, and then we went for sensing. Then we calculated the speed, torque, SOC, range and regeneration, braking, thermal model. After that, we moved to the time to collision and the blind spot detection of the ADAS safety. Then we did the 5 state of fault state management with bit mask fault and safe state cutoff. Then we moved over to UART command shell plus live Python matplotlib. Yeah. Hello. So as we can see, uh, first I'll show the output of the virtual terminal, and then we'll move on with the Python dashboard visualization. So as you can see, the brake is very less and the SOC is high, plus accelerators are also high. So because the accelerator is high, the speed keeps increasing over here. First it was 30, now it's 30.1, and it'll keep increasing. Here F represents the front distance, that is 203, as you can see over here, and left is 25. So the distance from the left side is very less of the vehicle. So on the left side there is a vehicle which is at a very less distance. Because of that, a warning is issued over here. So let me just move it over here. Yeah, so this is the blind spot detection left over here, as you can see. Yeah, and this is the blind spot detection right over here. Okay. Yeah, just move it over here. Yeah, and the front, if I reduce the front distance, you can see that, yeah, we get the fault over here. So this the LED which is connected to PB11, this represents any kind of fault over here. So because the front distance is very less from a vehicle, so it means the time to collision is the time to collision is very less. It's 0 second, and because of which uh, it can be an accident. So this LED goes on, and this PB8 represents the front collision. PB9 represents the blind spot detection of the collision from the left side or the blind spot, and PB10 represents the blind spot detection from the right side. So if I reduce the distance from the right side, you can see that, yeah, the blind spot detection right LED also goes on. Okay, so if you increase the distance from the left side, so this LED goes off. It means we are at a safe distance. Same over here, if we increase the distance, we are at a safe spot. But over here you can see the front distance is very less, so it can be some kind of an accident. Therefore the fault LED and this LED is both on. So let us increase this. I think it will go, both of them goes off, yeah. And the fault LED, if we increase the motor temperature, as you can see over here, if we increase the motor temperature, then this LED will go on, and the motor temperature increases. As you can see, before it was 31.1, now it's 105. So this it detects a fault. Okay, now let us reduce this. And yeah, and if the battery or the charge is very less, then also, for example, it is on before the, where is SOC, yeah, so before it was 98.5, 98.6, 98.6, 98.5. Now it will reduce, and you will see that this fault LED will go on. Just a minute, it will. Now let us move on to the Python dashboard. So for that, we'll go to the command prompt and we'll run this command. So it will connect and it will present us with this code. As you can see, the initial distance is moving a little bit late, yeah. As we have seen, the brake is very less and the acceleration is high, so the speed increases over here. It is a minute change but it's visible on the virtual term. As you can see, 30, first it was 30, then it's on 30.1, yeah. And if you see, because the speed is 30 km/h, so the mode is normal over here. As the vehicle keeps running, so this battery will keep on getting discharged, and the range also reduces. Here we have, because the range reduces, as you can see, the range will reduce, and as well as the battery percentage. The brake is 0%, and therefore we can see is accelerating, so the torque is 135 Newton meter. So as you can see, the battery is decreasing over here, and range also decreased over here. Acceleration, so acceleration is around 90%, and I think if we reduce the acceleration, it will get update over here. you can see the torque is also reduced and the acceleration is also reduced. If we increase the motor temperature, you can see the motor temperature, it will now increase. Yeah, so there's the fault has gone on. Okay, so it's up something 100 degrees Celsius, so there's a fault that is indicated. And if you, like, you can see on the LED over here also, let us reduce this. Okay, and let us increase the brake pedal, so you can see this will update over here. The fault will go, and yeah, the torque is negative because we are applying the brake. Now if you see, if we because of the regenerative braking, the range will now increase, and the battery will also increase, but it will be at a small rate. So it's 98.8% and 3 to 9 per kilometer. It will increase because the brake is very high. And if you reduce the acceleration, so the torque is negative 48 Newton meter, and the acceleration we have put it to 0 and brake to 100%. Yeah, so this is the maximum negative torque of 56 Newton meter. Yeah, as of now there is no fault. Now let us reduce the front distance. Okay, so as you reduce the front distance, this LED goes on, and there will be a warning if we reduce it more. You can see, yeah, so there is a critical warning, and the fault is 0x04 fault state. So there is a very high chance of collision, and the time to collision is 0 because the vehicle in front has come very close to us. Okay, so the whole dashboard flashes red because of the critical alarm. Now let us increase it a bit. And reduce this distance. As you can see, when I increase the front distance, the time to collision, it became 0.1, it increased. If we reduce it, let us increase the front distance. Yeah, so as you can see, 106 we have put the right side on 113 centimeter and on the left side 102 centimeter. So that is also a warning collision warning, it went off. Yeah, so there's no collision right now, but if we decrease the distance furthermore, there will be a warning. From the left side, this distance will reduce. It is a bit jittery over here right now. Yeah, let us decrease the brake, increase this. Yeah, so blind spot detection of the left side advisory alarm has been turned on, right? Now if we increase this distance and reduce this distance, yeah, so the blind spot detection of the right side is turned on over here. Now we also have an advisory over here. Yeah, blind spot detection from the right side, we have an advisory over here. So overall, yeah, as you can see, 3286, the range was increased because the brake was increased. Sorry, As the acceleration is increased, the range is reducing and the battery is also reducing. So this is the overall Python dashboard that we have built. I sincerely thank Emertxe for the guidance and everything that I've learned during this internship. So this is the overall project that I've done and learned over this period. It was a very meaningful experience. Thank you.